Test.
Hello, everyone. Good afternoon. Thank you so much for being here. My name is Jorge. I'm the CTO at Aragon One, which is the foundational team working on the Aragon project. And it is always so great to be back in Paris. This is a very special place for us. It's the first conference that Aragon ever did as a project. And last year, we actually saw the first version of Aragon 0.5, which is the first version of Aragon that uses Aragon OS, which is the same client that was released later in the year with on the mainnet. So for those that don't know, Aragon is a project that is building a digital jurisdiction that attempts to compete with land jurisdictions such as France, Spain, or Switzerland in value creation and allowing borderless value creation and company and organization creation. It's built on the Ethereum virtual machine, and as of this morning, we had 353 DAOs running on the Ethereum mainnet. So last year, we kind of presented that this might be possible. Right now, there are 350 DAOs live. And it's available both on the web and on mobile right now. And if you want to get the pure decentralized application experience of Aragon, you can use it on the desktop as well. But what I want to talk about today is about Aragon voting. Because voting, by default in our Aragon organizations, voting is the default root authority of the DAO. What that means is that all the decisions in the DAO that are important enough start as the voting app being the root authority, and then that voting interface can give the decision power to other entities. What it means is that there's a lot of voting going on, so we care very deeply about voting. And as of right now, there have been $1 million protected by Aragon voting, and it hasn't been broken yet, so we're very happy about that. But today, the talk is going to be about how to improve voting. But there's a concept that we built into voting that we're actually not going to be changing. That is called forwarding. And you may think that if a lot of things go by voting and governance structures get like more and more complex because you have like a vote that triggers another vote, this may get very complicated to operate and to know what do you have to do if you want to perform an action. So thanks to forwarding, this is something that in the Aragon client automatically can calculate what needs to happen. So you just have an intent. I want to upgrade my DAO to the latest version of Aragon OS, or I want to transfer 100 tokens out of this DAO's vault, and you just do that as if you had complete power, and then the client will know what scripts it has to create so that those scripts get voted on and the intent that you had actually happens. So, Aragon Voting V2. We're kind of calling Aragon Voting V2 to like an umbrella of different improvements that we want to ship at the same time. But the two major improvements that we want to do and that we're changing is, number one, we're going to be removing the mini-me token requirement for all Aragon DAOs. This is something that it's been great for us up until now, but we've been getting a lot of existing projects that have a token or protocols that have a token and also want to use Aragon. And right now it's like you kind of need to wrap your token into like a mini-me token, and this is something that is becoming a UX hurdle. And we will go deeply into why we're doing that. And the second thing that we're doing is that we want to make voting really, really cheap. And by really cheap, it's like voting has to be so cheap that it doesn't even matter if you have to pay for it because the cost is so low. It could be virtually free. And this, of course, will give us support for all ERC20 tokens, and it will require us to do most of the voting off-chain so that we don't have the cost of voting to all of the nodes of the network. Regarding mini-me, a bit of background on why we have to use mini-me. Mini-me allows us to solve the double voting problem. The issue with ERC20 tokens in regards to voting is that the ERC20 tokens are completely fungible. A token doesn't have a serial number, so if you don't take any active measures, you don't really know if a token has voted only one time or if they have voted twice with the same token. And if you can do it twice, you can do it infinitive times. So the idea would be, if you don't take any measures, you have your tokens in one account, you vote for the proposal, then you move them to another account, you vote for the proposal again, and that until you basically win the proposal. So there are like two things that people have done to resolve this issue. One is required to lock the tokens in order to vote. So in order for you to vote for the first time, you have to send your tokens to another contract, and then your tokens get locked there until you either withdraw your vote or the vote is over and you cannot vote again. This is a major UX issue that people really, I mean, there are enough problems with getting people to vote, and if you have to make them send their tokens somewhere else, that's like a bigger issue. And then there's the Minimi approach. And what Minimi does is it basically keeps the history of token balances that anyone had in the token. So in a normal token, you just know what the most recent balance is for someone, but Minimi actually keeps track of, okay, if you transfer tokens at this particular block height, I know how many tokens you had before and how many you had after. So a voting app can ask for token balances at the end of a block number, and for that, a token can only be in one place at the end of a block number. So for this, for kind of getting this token snapshot in without actually having to put the checkpoint in the token contract, which is pretty expensive, we've done something that is called EVM storage proofs. That we're using them for voting, but this is actually usable for a lot more use cases. What you want to achieve with EVM storage proofs is you want to prove to a contract, in this case it would be the voting contract, what a particular storage value in another contract was at a past block height. In a way that you can effectively have checkpointing for any storage value of any contract at any block number. It uses EIP 1186, I believe, or ETH-GET proof that allows us to use. This requires archive nodes for generating proofs, not for verifying them. Allows us to get a proof in two parts that we will see now. So first we have the account proof. And in the account proof is when we go from the block hash of the particular block number where we're checkpointing to the storage root of that contract that we're interested in. So here we start with the block hash that we take it as true. We can get the block hash by running the block hash subcode, and then you kind of have to follow the unicorn if you see it. You start from the block hash at that block height. You submit the entire block header. You verify that actually that block header hashes to the block hash that you already have. Then from that block header, you can extract the root of the state trie. This is the trie that has the state of all the Ethereum accounts for that at that block number, and from there you can do a Merkle proof of from that root until the account that you're interested in. In this case, it would be the token contract that you're interested in its storage, and then once you get down to that account, you prove the state of the account at that block number. You can extract from here the storage root for that. For that contract at that block height. And once you do this once, you can actually cache this and use it for all the proofs, for all the storage proofs that come now for particular token balances in this case. And with this is very simple. The root that you have is the root of the storage trie for that contract. So in case of a token, it would contain the token balances, the snapshotted token balances for that token. So what you have to do there is you just need to know at what storage slot a particular token holder balance is, and you just perform a proof there, and effectively you get the checkpointed block token balance for that token holder. So this is the first part of the mechanism. You can see on the right, you can't really see, but this is like the entire proof that you split it in two, and on the left that you definitely cannot see is the actual proofs that you submit to the blockchain. The upsides of this is that you can take any ERC20 that is already deployed and basically convert it into a mini-me. You can ask for checkpointed block balances, token balances, and the greater thing is that snapshotting doesn't impose a cost on every transfer. This is like the main issue with mini-me right now, that you basically duplicate the cost for token transfers because you don't need to just pay for moving balances, but for actually making sure that you have a checkpoint at that height. The main issue is that these proofs are pretty expensive right now. They're like 500,000 gas, and then like some minor details like, okay, you can only start proving this for the last 256 blocks, and something that you need to be careful because you're reading raw storage, and the EVM wasn't designed so people could do this, so you need to be careful with this. So with this, we get into the second part. It's like, how can we make voting very, very cheap, especially if we're gonna add something that requires verifying a proof of 500,000 gas that you have to do for each vote. And the pattern that we're following here, it's something that is called optimistic contracts that have been kind of put a name by Dean, or like Twitter's favorite troll. And the idea of optimistic contracts is that you basically offload the computation from all the nodes in the network. So say if you have to do a compute-intensive transaction, everyone in the network will forever have to replay the transaction to make sure that the result is actually correct. The issue with that is like when you are doing, like you're repeating that, and that's why it has such a high cost. Optimistic contracts actually offload that computation to just one incentivized party that will commit to a particular result of computation, and they will say, okay, this is the result that if you run this function, you will get, and I will bet 1 ETH that this is the result. Then other people, other challengers, can check locally that that's actually the correct result, and otherwise they can submit a challenge. And here I prepared some code of how the optimistic pattern looks like. I will actually upload this later as a gist. But the gist of it is someone commits to a result, they provide the input to the computation, and then if someone has some time to challenge it, if no one challenges it after a certain amount of time, you just take that as true because anyone could have profited from the opportunity of saying that that computation was actually false and performing the computation on chain. So with this idea of optimistic contracts we've built this protocol, this layer 2 protocol that we're calling VRP, which is the voting relay protocol. And the idea of VRP is very simple. Right now, Aragon voting just works like, imagine that this is like a national election, and in Aragon voting right now, everyone that wants to cast a vote, you just send it directly to the government, and the government counts 1 by 1 vote. This is a very inefficient way of counting votes. So what we do is like, we kind of batch people into like putting their votes in ballots. A lot of people read the votes in these different ballots at the same time, and then you kind of like sum the partial tallies and you get your final result. And this is kind of the same idea. Rather than processing every vote on chain individually, you just have this entity that is called like a relayer. They will get all the votes, they will verify the votes, and then they will provide a commitment saying, okay, I have all these votes here, and I commit that the result of verifying all the balances here and summing all these votes, is going to be X amount of votes. So you take this as true unless someone submits a proof, and if no one submits a proof, you just basically take that partial tally as true, and you don't even verify any vote. But again, anyone could have like said, okay, this is bullshit. If you count this vote on chain, you will see that they summed wrong, or this entity actually had 0 tokens instead of 1 million. And actually, version of VRP that we've been posting now, we're calling it simple voting relay protocol because we only allow one relayer to relay votes at the same time. This allows us to simplify a lot of issues in regards to relayers griefing each other, with like voters sending votes to multiple relayers. And this central relayer needs to be, can be either centrally appointed, like the organization said, this entity is going to be our relayer, or it can be auctioned because these relayers can earn fees. This may be a centralization factor, you may say. The good thing is, like, even if there's just one relayer that can relay votes, they still will be penalized if fraud is detected. So they cannot commit fraud. The only thing is that this relayer could censor some votes that they don't like, but of course voters can directly submit their vote. And people may look for solutions in case that someone is actively, a relayer is actively censoring, to change the relayer for future votes. The bottleneck that we found with SVRP is that the naive implementation of optimistic requires you to pass the input of the computation that is going to be optimistically executed. You have to send it to the blockchain, and basically you need to log it. This is the way that you ensure that the input data is available, because you actually need the input data to perform a fraud proof. So a simple idea would be, okay, then rather than submitting the full proof, like the full input, you just commit to the hash, and then you relay, like you can rely on the relayer making that data available for anyone to just get that data from IPFS or whatever, and then submit fraud proofs. But here we have like a pretty interesting data availability issue, in which the relayer actually doesn't need to, they can submit a fake hash of the input if they don't have to submit the full input, so that no one can actually look for that. And the issue with that is, like, if no one has the input, they can commit fraud, because no one can submit a fraud proof if you don't have the input that matches the hash. But the bigger issue is that the smart contract doesn't know what is going on. You cannot prove to a smart contract that a particular piece of data wasn't available. And even if you add like a mechanism that, okay, if someone asks for that data, then the relayer has to provide it, because the smart contract doesn't know that that data actually wasn't available. This is an opportunity to grief the relayer. So you have like a big issue not making the data available with log. And this is what creates the bigger bottleneck, because you actually have to pay 68 gas per byte of input data, which for voting, it's quite, the cost, it's actually what becomes the scaling bottleneck. So with this, our latest research has been around this new mechanism that we're calling optimistic data availability, and we're actually doing like another relay protocol that we're calling AVRP. And the idea here is that rather than having just one validator, like one relayer that can submit votes, you actually have a set of n validators, and that could be a number like 11 or whatever, and you actually decide randomly who of these validators will be appointed the relayer per each period of time. But they don't know beforehand. So the idea here is that each of these validators should be keeping the entire input data in case that they became the relayer randomly, and they can submit the computation and earn the fees. But what you achieve here as well is that all of these validators, you kind of know, and they actually need to sign a message saying that they have the data before someone can submit it, that they are able to submit a challenge. Also, if even just one of these validators makes data publicly available on IPFS or whatever, then anyone can submit challenges. So you kind of move this, you don't have to put the data in the transaction, but you still get into a situation that unless more than 2/3 of the validators conspire to keep in the dark the honest validators, and there's this one person that is willing to submit a challenge, then you're actually okay. So with this, we just made the first iteration of simple voting relay protocol, open source today. This is a fork of the current Aragon app. It's still like a proof of concept, but it's actually working with storage proofs and everything, and we're super happy to be advancing on that regard. And yeah, as a kind of like a TLDR of the upgrades that we're doing to voting, We're using storage proofs to remove the minimum requirement and get snapshotted token balances in a way that doesn't impact all the token transfers. And we're working on these voting relay protocols to aggregate votes off chain and actually just perform the minimum amount of computation regarding the vote tallying on chain and still get elections that you can trust that they weren't rigged. So yeah, that's all the research is happening in the Aragon forum. That you have the URL there, and we have work opportunities to come work with us on these types of problems if they're interesting to you. Yeah, thank you. Can I take questions? Yep.
For the challenging phase, what time modes, the order of magnitude of the time modes that you are working? Are you talking about hours, days, weeks, months? For the challenging, so when one challenge and how this challenging, how long does it take so that you consider, how time happens until you consider that the voting is valid?
Yeah. There hasn't been like a lot of research into finding what these challenge periods have to be. The variable that you have to achieve is that what is the minimum amount of time that you have 100% certainty that you're going to be able to include a transaction on chain. And then the reward for the validator needs to be like 1 or 2 orders of magnitude more than the cost of getting the transaction included on chain, because gas price fluctuate entirely, and this could actually be a risk if the reward for a challenge becomes too low in regards to what it costs to get the transaction included, because the gas price spikes. That could be an issue. So I don't have a specific answer, but I would say like in the order of magnitude of days.
Thank you for the talk. Do you think that your data availability solution could be used for other off-chain scalability protocols such as Plasma?
We've been very focused on our own research, but I think it could be an interesting thing to explore. At the end of the day, here, if you compare it to like a blockchain type protocol here, like the relayer that you select randomly could be like thought of as the block producer or the block author. So I think it could definitely be used. Yeah.
Do you have an estimate for when you might be able to get this out? And if it's going to be a while, what can people do to get going quickly at this point?
Yeah, so the basic implementation of the protocol, SVRP, it's open source now. Like the proof of concept is working, but again, as I said, this only gets us a 10x improvement over the current voting implementation. AVRP is when you actually start getting like 3 to 5 orders of magnitude more scalability, but that's definitely, there's a lot of uphill implementation work there, so couldn't say this year maybe. Yeah, thank you.